Okay, so for today, we're going to continue working with our factoring using our difference of squares. But what we're going to do is we're going to kind of throw in a couple more ideas here, meaning maybe we have to, instead of factoring it once, maybe we have to factor something twice. Maybe we have to factor it 3 times. So we're going to look to possibly apply maybe a technique more than once, or apply some of our different factoring techniques all into one. So for the first example here, let's say that we had the question b to the 4th minus 16. Okay, so let's say this was the problem that we were looking to factor here. So the first thing we look at is always GCF. Now we realize that there's no GCF between b to the 4th and 16, so we can't do that. But we do realize that this is a binomial, so I can definitely factor this using the binomial method we talked about yesterday, the difference of squares. We do see that one of them is negative, and these are both definitely perfect squares. If I were to take the square root of b to the 4th, I would get b squared. If I were to take the square root of 16, I would get 4. So they are both perfect squares. So what that means is that when I factor it, I put the first term and the second term in the first parentheses, adding them. So it's going to be b squared plus 4. And then in the second parenthesis, it's going to be b squared minus 4. Now, normally we would think, oh, well, we're done. We're finished. We've factored it, right? But the problem here is that when I look at my two factors, the first one I definitely can't factor again. But the second one here, I can factor it again. And why can I factor it again? Well, because it's a binomial, 2 terms. One of those terms is negative, and both terms are perfect squares. That's also why we can't factor the first one. Yes, the first one's a binomial. Yes, both terms are perfect squares, but not one of them is negative. They're both positive. So this one here, this can't be factored again. But this term here, this term can get factored one more time. So I basically just do the same thing that I did up here to this parenthesis here. The front parenthesis is going to stay the same. I'm just going to kind of bring that down. That's going to be b squared plus 4 again. But just like we did up top there, we're going to do the same thing down here. I'm going to take the square root of b squared, and that's b. I'm going to take the square root of 4, and that's 2. So as we see, they are both perfect squares. So I can refactor this whole second parenthesis to be b plus 2, b minus 2. But like we said, we can't forget the b squared plus 4 in front. So my final answer here is going to be b squared plus 4, b plus 2, b minus 2. Okay, so again, remember, the reason we can't factor this first one again is because both terms are positive. We need one of the terms to be negative in order to factor it using our difference of squares. And the reason I can't factor this one again using a difference of squares is because neither of these are perfect squares. B is not a perfect square, and neither is 2. If I were to take the square root of them, I would not be left with a whole number. So this is why this would be my final answer here. Okay? So let's try another one. Same concept, though. Let's say I had 625 minus x to the 4th. Okay? So same idea. I see that it's a binomial. There's no GCF. But I should recognize that they are both perfect squares. Meaning, 625, if I were to take the square root of 625, I'm going to end up getting 25. If I were to take the square root of x to the 4th, I would get x squared. So they are both perfect squares, meaning I get to put them inside the parentheses. So it's going to be the first term plus the second one, and then the first term minus the second one. But again, first term can't be factored again because they're both positive, but my second one can. 25 is a perfect square. X squared is a perfect square. They have a minus, So I can factor this one more time. The square root of 25, that's going to give us 5. The square root of x squared, that's going to give us x. So this second parenthesis can be factored once more to be 5 plus x, 5 minus x. Again, I can't forget my first parenthesis, so I have to bring that down. The 25 plus x squared. And then this right here would be my final answer. 25 plus x squared times 5 plus x times 5 minus x. All right, so I have 4 problems here up on the blackboard. So I'd like you to pause the video, take about 5-10 minutes, try some of these on your own, and then unpause the video and see if you got these correct. Okay, so hopefully these are the answers we got here. So for the first one, if we take a look at it, the square root of y squared, y to the fourth would be y squared. The square root of 1 is always 1. So we have y squared and 1, both perfect squares, so it would be y squared plus 1, y squared minus 1. Recognizing over here that the square root of y squared is y, and again the square root of 1 is 1, this can be factored again to be y plus 1, y minus 1. The y squared plus 1, that just stays as y squared plus 1, and that would be my final answer. For the second one here, I tried to trick you. Yes, it can be factored by difference of squares. The square root of 4a squared is 2a squared. The square root of b to the fourth is b squared. So it would be 2a squared plus b squared, 2a squared minus b squared. But then when I look at my second parenthesis, 2a squared cannot be taken a square root of. 2 is not a perfect square. So I can't factor this again. This is just the final answer here. Okay, so you do have to be careful. Just because you see a exponent here, or just because you think, oh, maybe I can, it has to be a perfect square. This has to be a perfect square, and 2 is not a perfect square. So I cannot factor the second one again. For the third one, square root of 81 is 9. Square root of x to the fourth is x squared. So I have 9 plus x squared, 9 minus x squared. I look at the second one, square root of 9 is 3. Square root of x squared is x. So it's going to be 9 plus x squared, 3 plus x, 3 minus x. Same thing with the last one here. Square root of 16y to the fourth is 4y squared. Square root of 1 is just 1. So it's 4y squared plus 1, 4y squared minus 1. Take the square root of 4y squared, that's 2y. Take the square root of 1 is 1. So that part becomes 2y plus 1, 2y minus 1. And I keep that 4y squared plus 1. Okay, so that was one or two or a couple where we did the difference of squares multiple times. But like I had said in the beginning, there could be times where we have to do multiple different techniques, meaning maybe we do GCF and difference of squares, or maybe we do GCF and grouping, or GCF grouping and difference of squares. So there's a lot of different things that we have to kind of look at here. So, for example, let's say we had the problem 5x to the fifth minus 45x. So, first things first, we always check to see, is there a GCF? And hopefully we recognize that, yes, there is a GCF here. The GCF of this would be 5, because they both have a 5 in common here, x. Take that GCF out. We take each of our terms, divide it by 5x, we would be left with x to the fourth minus 9. Okay? So once I take that GCF out, I now only look at what's left inside the parentheses. X to the fourth minus 9. Well, I should recognize it's a binomial where one of my terms is negative, so let's see, can this be factored by difference of squares? And I recognize that it definitely can, because when I take the square root of x to the fourth, that's going to be x squared. When I take the square root of 9, that's going to be 3. So when I factor this out, it's going to be x squared plus 3, x squared minus 3. Don't forget to bring down the GCF of 5x. So always bring that down. And then I just take a look-see and I say, all right, can x squared plus 3 be factored again? No, because we know that a binomial has to have a negative part, and none of these are negative. Then I look here and I say, well, could this be factored again? It does have a negative, but the first term is a perfect square. 3 is not a perfect square. So this can't be factored again by difference of squares. So I would just leave it. So this would be my final answer. Okay? So let's do one very similar to that in terms of where we would do multiple different techniques. This one we did GCF, and then we did difference of squares. So let's take a look at one like this. Let's say we had 7x to the third plus 21x squared minus 7x minus 21. Okay, so first thought here should always be, hopefully you said it with me, GCF. Always look to factor out a GCF first. So we look at my coefficients, 7, 21, 7, and 21. Well, that should be a pretty simple GCF. We know that that has a GCF of 7. I look at my variables, x, x, x. This doesn't have an x, so I can't pull an x out, so the only GCF is 7. So I'm going to then take each term divided by 7. So the first one would give me x to the third. 21 divided by 7, that's going to give me 3x squared. 7x divided by 7, that's going to give me x. And then 21 divided by 7 will give me 3. Okay, so now I have a new polynomial here. I factored out a 7. Again, I only look at what's left inside the parentheses. I don't worry about this GCF. I'll just bring this down at the end. So looking inside here, well, I see a 4-termed polynomial. What's my method of factoring a 4-termed polynomial? Hopefully you said grouping, because yes, grouping is the method that we want to use here. We're going to group the first 2 terms. We're going to group the second 2 terms. I'm going to pull a GCF out of my first term here, or my first 2 terms. So the GCF between x to the third and 3x squared, that would be x squared. What's left? X plus 3. I do the same thing to my second pair. What's the GCF between negative x and negative 3? Well, remember what I always say. If this first term is negative, you should pull out a negative number. So in this case, it's going to be a negative 1. So that's going to leave me with x plus 3. Well, I notice that I have twins here, which is exactly what I want. So I'm going to take my 2 GCFs here. Those are going to go in one parenthesis, x squared minus 1. And the twins will go in the other parenthesis, x plus 3. Don't forget about the 7, though, that we took out in the beginning. That has to come down. And you'd think, oh, great, we're done. But always check what's left inside your parentheses. Because when I take a look at this first parenthesis, hopefully you recognize that here, I can factor this again. It's a binomial with a minus sign, and both terms are perfect squares. The square root of x squared is x. The square root of 1 is 1. So this parenthesis right here can get factored again to be x plus 1, x minus 1. I can't factor x plus 3 because it's not; these aren't perfect squares, and there's no minus in the middle. So that's just going to stay as x plus 3. And the 7 was already factored out, so that can't get factored again. So this would be my final answer. So you always, 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 always have to ask yourself, after you've factored, look at your parentheses and say, can this be factored again? Could I factor this using a different method? Can this be factored by our trinomial methods? Could it be factored by grouping? Could it be factored by the difference of squares? Could I factor a GCF out? All right, you have a lot of different possibilities that you can use, so you have to really make sure that you're checking them all. If you don't fully factor something, you are going to get points off. So you have to make sure that you fully factor it. Okay, so again, here are 4 problems up on the blackboard that I would like you to try on your own. So pause the video here. If you need to rewind the video to have me go back over things, do that. But I really want you to try these on your own. See if you can solve these on your own. Okay, so hopefully these are the answers that we got here. So for the first one, pretty straightforward one. We are first going to factor out a 2 to get y squared minus 25. Then we recognize that these are both perfect squares. We have a minus here, so the square root of y squared is y. Square root of 25 is 5. So we have 2, and then we have y plus 5, y minus 5. For the second one, we don't see a GCF between any of them, so we go straight to doing our grouping. So we group the first 2, group the second 2. The GCF of the first 2 is m squared, so then we're left with a 2m plus 1. The GCF of the second one is a negative 25, so we're left with 2m plus 1. We see that we have a twin, so we take my 2 GCFs of m squared and minus 25, put those together. We take the twin of 2m plus 1, put that. But then we notice here, okay, we have a binomial with a minus in between, and both of these are perfect squares. So the square root of m squared is m, the square root of 25 is 5, so the first one is going to turn into m plus 5, m minus 5. The second one will just stay as 2m plus 1, and then that would be my final answer. For this one down here, kind of ran out of space, but that's okay. I'm going to first factor out a 6, because I realized that they both have a 6 in common. So once I factor out a 6, I'm left with x to the 4th minus 16. Once I'm left with that, then I say, okay, binomial, minus in the middle, take the square roots. Square root of x to the 4th is x squared. Square root of 16 is 4. So I'm going to have 6, x squared plus 4, x squared minus 4. But then I look at this one again, binomial with a minus in the middle. Square root of x squared is x, square root of 4 is 2. This can get factored again to the x plus 2, x minus 2. So this one, this one kind of included a lot of different factoring here. And then for the last one, I gave you a nice little easy one here. No GCF, so we start by grouping. We group the first 2 together. We get r squared. What's left is r plus 6. For the second one, the GCF is 11. What's left is r plus 6. I see a twin. Take the 2 GCFs, put them together, and then there's nothing else I can do. This isn't a difference of squares, so I leave it as r squared plus 11, and the r plus 6, and that would be it there too. Okay, so the last thing I wanted to talk about very quickly, because we've done it in every lesson so far, is solving. So let's just say we had an equation of x squared equals 121. Okay, so let's say that this was the problem that we were looking to solve. So if we remember our steps for solving a quadratic function, remember, step 1, sorry about that. Step 1 is to set the equation equal to 0. Get the equation to equal 0. Pretty simple step here. Subtract the 121 from both sides. So I have x squared minus 121 equals 0. Now my equation is equal to 0. Step 2, factor. Okay? I have a binomial with a minus. I can factor this by difference of squares. Take the square root of both sides. The square root of x squared is x. The square root of 121 is 11. So this becomes x plus 11, x minus 11 equals 0. And then step 3 is to set each factor equal to 0 and solve. So I'm going to take each of my factors, the x plus 11, set it equal to 0, the x minus 11, set it equal to 0, and then I'm just going to solve. So one side I'll get negative 11, and the other side I'll get 11. So I would set my answer, or say my answer was x is equal to the set of numbers, negative 11 and 11. Okay? But like I said, this is a little bit of a quicker one just because we've done this for so many lessons now. We should know our 3 steps to solving any of our quadratic functions. So hopefully we understand that. You will see it on the homework, so you will get a lot of practice with this.